with NaiveBayes algorithm, what it is basically, and then we can continue to the coding part of it. So let's say we have some data. It looks like this, wherein we have our x, which looks like uh, x1, x2, xf. Here are n samples, and here are f features. So the shape of it is n by f. This one x1 is a feature, is value of all the samples for that particular feature x1. Um, and there would be y, which is the target variable, which would be basically look like a column vector of size n. Its size would be something like this. And let's say we assume that number of classes equals to 2 to start with. Then here I'll also tell you that one feature vector, what is a feature vector, which will be a vector for any particular sample. Like say, let's say a sample, ith sample in the data x is nothing but a set of x1, x, or rather I should say x1, I, x2, I, xfi. This is a feature vector. So now let's uh, these were some introductory notations we'll use. Uh, so with Bayes, the problem statement here is on the basis of any particular feature vector of a sample, we need to predict class of that particular sample, right? So then one thing we need to understand is to start with Bayes theorem. So I'm not going to uh, talk you through derivation of Bayes theorem. There are some good videos on YouTube you can find to do that, but I'll just state the Bayes theorem and then we'll go along how to use it. So Bayes theorem says that if you want to find a probability of any given A, any event given A, any event, if you want to find the probability of any event A given that event B has already happened, so that this can be calculated as probability of event B given A has happened multiplied by probability of A divided by probability of B. So this is basically the Bayes theorem, and we want to use this to do our classification problem right now. So how do we use it is, let's say that A is Y and B is X. So what we want to evaluate is probability of Y given X, which can be calculated as probability of X given Y times probability of Y divided by probability of X. Now if we expand this equation, it can be here we can say that X is formed of um, X is a, here we are assuming that Y and X are vectors and classes of a particular sample. So X, capital X, can be noted as a set of x1, x2, xf, vector of length f, which is the number of features. So we can break this particular component in the equation as a product of probability of x1 given y times x2 given y and so on times p of y is whole divided by p of x. So now, if we have this probability of a class given X, um, so if there are n number of classes or two classes in Y, we'll calculate this particular value for those two different classes. Let's say Y0 and Y1 are two different classes. So we'll calculate P of Y0 given X and P of Y1 given X. And out of this, whichever number, the probability of Y1 or Y0, whichever is greater, we'll choose that particular class as the prediction for that particular sample. So to simplify it further, we can say in Python, and the operation of finding out the um, maximum probability in from a vector of probabilities or an array of probabilities is using argmax of P of Y given X for maximum Y. This will be equals to P of X1 given Y, P of X2 given Y, so on, P of Y divided by P of X. Now, once we have this, so we can say that this particular component P of X will be constant throughout. So we can also write this as P of X1 given Y, P of X2 given Y, so P of Y. Now, uh, this is nothing but basically a product of a lot of probabilities. So probabilities are always between 0 and 1. If you multiply a lot of those numbers, it will become a very small number. So this have a risk of doing underflow, going underflow. Therefore, we take log of, or rather, I should write it as argmax log of probability of Y given X equals to max. So if you take log of this entire expression, it will just become a sum of the individual logs. So it will be log of P x1 given Y plus log of P x2 given Y plus so on log of P Y. Now what we can do is we need to understand what are these individual probabilities, like P of x1 given Y or P of x2 given Y. So instead we'll say P of xi given Y. And what is Py? So Py is nothing but the frequency of the class I, which would be nothing but the total count of samples where class I occurs divided by class, I think, of that class, I should say. This would be divided by the total number of samples in the data. And P of x of I is, um, it can be seen as, um, uh, I should call it as um, Gaussian probability density function of xi feature for that class. So in this scenario, we are talking about a particular class, let's say y0. So for y0, whatever samples have y0 uh, class, we'll choose those samples, and for that particular feature I of for the classes that are equal to y0, we will will calculate the probability density function, and from that we'll find the likelihood of it. So let me draw a diagram. Let's say um, xi is here for class y0. So let's say its probability density function comes out something like this, right? Now, if you say what is the probability of x1 given y0? So x1, let's say x1 value is 10. 10 comes somewhere here. So this particular value is the likelihood that will give this term, probability of x1 given class is 0. Sorry, class is y0. So that is how we'll have to approximate for each class and correspondingly the samples that belong to that class and each feature. Each class and each feature will have to be approximated by a Gaussian distribution. So we'll have to basically calculate a mean and variance. Let me draw Gaussian distribution equation. Okay, so here's a Gaussian distribution function. You can see that it gives a distribution as 1 over, where you can understand that mu is the mean of the variable, sigma is the standard deviation, sigma square means variance. So we'll use this formula to approximate any particular features values for particular class. And using this approximation of a Gaussian normal distribution, we'll calculate the likelihood of that particular feature value given that class. And hence, and that is the way that we'll be able to calculate P of, you'll be able to calculate P of x1 given y for each set. So here P of x1 given y will be, so when we are doing it for y0, a class y0, this will be P of x1 given y0, P of x2 given y0, and so on, and P of y0. P of y0 will be calculated with uh, count of number of y0 occurrences in the training data divided by number of samples, total samples. So it is basically a frequency of that particular class. And so yeah, once we have done this, so to calculate this likelihood, we'll need, so let me write down the formula here. It is 1 by 2 pi sigma square under root times e to the power minus x minus mu square divided by 2 sigma square. So this is the formula. So to do this, we'll need to calculate sigma and mu for each feature, each class. This will be how we'll have to fit our model. Once we have these, we can do the predictions. So I hope this is clear to much extent. The Bayes theorem is just a starting point. That's why I'm not going to the derivation of it. From Bayes theorem, how do we approximate? We find out the probability of y given x. We have simplified the equation till this point, and here we need to understand how do we calculate all these likelihoods, p of x1 given y0, x2 given y0, etc. And we'll have to see how do we do it. So yeah, now I'll just continue with the code. Jump into the code. All right, so getting into the code, uh, I'll just quickly introduce you to the data that I'm using. But mainly in this video, we'll be coding the algorithm from scratch. So more about data, we can go through it once we are running the model and getting the results. So overview is, this is a classification data where you have to predict the personality of a person for whom you have all these features available: time spent alone, stage fear, social event attendance, going outside, trained after socializing, friends circle size, post frequency. So this is the data from a Kaggle competition, and mostly all the features here are categorical or ordinal in nature, and with these features we have to predict whether the person is extrovert or introvert. So I've done quite a few exploration on the data, and then also some pre-processing, which I'll probably go through it after once I have completed the model. So let me just minimize these one. Okay, so basically we have a data which is x inputs and y. So we'll have to we have to write a model. Basically, in this NaiveBayes, we don't need any initialization because there's no hyperparameters to the model basically. Therefore, we can directly start with fit. So when we call fit for any model, we pass inputs and outputs to it. So to start with, we'll need to unpack the dimensions of x, features equals to x dot shape. Then we need number of classes equals to, or maybe first let's say we initialize classes themselves. Empty dot of y. Once you have the classes, this will give us a list of classes. Once you have that, we will calculate number of classes is number of classes. Now, once we have all the classes, we need to calculate initialize the mean, variances, and for classes we need to initialize priors for each class and each feature. So initialization can be done as self mean. These variables we can use. So all these uh, uh, learnings from the model we can initialize it as zeros. So here this would be of the shape n classes by n features, because for each class, every particular, let's say for class y0, each feature will have its own mean, its own variance. Therefore the size of the shape of this self dot mean would look something like this, and we can type np dot float 64. Something similar for variance. It would be of the same shape. The priors would be of size and classes, because for each class there will be only one prior probability, that is the frequency of it basically. Therefore we can say it as np dot zeros, number of classes. We can fix the d types. Now let's assign value to these attributes for idx and class n. Right, let's go classes. We'll enumerate on all these classes. For each particular class, we'll first have to filter index into the data where y equals to c. So this will give us the a Boolean vector of indices wherever the a Boolean vector of the length n samples. Wherever the y is equal to c, it will be true, and therefore we can index into the x with this Boolean list of the indexes, Boolean vector basically. So we'll give x square will give us a uh, x data where the classes are only equal to c, that particular class. Once we have that, we can assign self dot underscore mean c cth class. So you see there is the first index is the class. So for each class we'll be assigning values. C equals to np dot mean dot c. We'll take mean across for this x where c variable, and we'll mean it on the axis 0. We are collapsing the axis 0. So for each feature we'll get a mean here. Variance for class C is np dot var x where c x is equals to 0. Alright, now self dot price c is nothing but length of x where c divided by n samples. So we have all these three uh, parameters defined, and I think um, That's all we would need for this. Yeah. Okay, I made a mistake here. Here, instead of class, I should be doing indexing with the indexes. My bad. So for this row and all the columns, we are assigning values from this calculation. Okay, now once all this is done, we move on to predict. So to predict, we pass in input x. X is a vector of is a multi-sample inputs coming in. So for x and x, we dot underscore predict x and so each self dot predict call for each sample, each sample x in x will get a prediction, basically a class for each of those. So this will become a array of number of samples that are present in X. Basically, maybe we can say now we have to define underscore predict. So what is that we are going to do in underscore predict? So whenever we get a sample for that particular sample, we need to right. So to uh, uh, write the code for underscore predict function, which is predicting classes for a particular sample. Let's quickly recap the expressions that we learned in the theory. What code it is. All right. So yeah, so here you see that at the end of our expression evaluations, we reach to a point where we are calculating log of p y0 given x. Right, so this p of y0 given x is a posterior probability for class y0. Similarly, we need to calculate posterior probability for each of the classes y0, y1, whatever the number of classes are there. And these are the likelihoods. So these are the likelihoods given in the class, that particular class. So we need to first initialize, switch back to the code. All right, so posterior variable will show the probabilities for each particular class. This should be of the length and classes for each sample, right? So now let's iterate on the classes for for each class. We need to calculate the posterior probability. To calculate the posterior probability, we need priors. Prior equals to priors of that particular index. Then we need Uh, so right now, this is the in our expressions. This is the posterior probability. P of y0 is prior probability, which we will extract from the self dot underscore prior attributes. And this sum of all these log of probabilities is the sum of all the likelihoods logarithm log basically. So this is the expression that we need to calculate. This we can directly extract. We have already calculated. So we are going to next calculate this part, likelihood of each variable, each feature for that particular class, given that particular class for that sample. So say posterior is np dot log, or this is np dot sum of np dot log of. So we need to define a helper function wherein we'll pass the index of the class and the X sample, all the features from the X sample, which will return us the uh, Gaussian probability density function for each of the features from this class, and that we can use. So this would return the probabilities. This would basically, we can say that this would returns probability of X given Y0, or whatever X given X given, yes, so basically X given C. Therefore what we need to do is we have prior X given C. So for this particular class, what is the likelihood of all these features individually? So this would be nothing but a vector of shape and features, and then we can take a log of all of those and do the summation. So we'll need to define this helper function later. Posterior is equal to posterior plus prior. This is where we sum the prior probability of that particular class. Probability of class C. Once we have done this, posterior dot append posterior. Once we have done this for all of the classes, once we have done this, we'll need to calculate np dot argmax of posteriors. This would give us the index of the uh, highest probability out of it. So we will need to get the we'll need to get the class from that id index. So therefore we return this class of the highest probability from this posteriors. Now we are left to define this Gaussian PDF function takes class index and the sample as input. So what does it do here? So to calculate to find the likelihoods, we'll need means, where's variables, and then so mean is nothing but 0 dot underscore mean of for that idx. Idx equals 0 dot underscore idx. Now um, if you remember from our formula, let me quickly show you that formula once more. Yeah, so this is what the formula looks like, right? We'll need to calculate this expression 1 over square root of 2 pi sigma square, which is the variable for that particular feature for which we are evaluating the likelihood. X is that xi, the value of that particular feature which we have received from x. Mu is the mean of that feature, and we need to calculate this entire expression. Therefore, we will calculate a numerator and denominator. Denominator is nothing but 1 over 2 times np dot pi times var squared. So whatever is happening here, it will all be a vectorized calculation. Sorry, it is variance. Sigma square means it is variance, not variance squared. Therefore, this is the denominator. Numerator will be exp exponential of or exponential of minus of, right? Mean squared x minus mean squared by 2 into variance. Sorry, I keep looking at the formula back and forth. So divided by 2 times variance. So negative of x minus mean. So x minus mean is x is a vector of f features. So values f values column vector, and mean is also of the same dimension. So they will do element by subtraction, square each number, and then divide by the variance of 2 into variance of each particular feature. And so this will give you a of size and features, a vector of size and features, and this will give you also give you a vector of size and features. So I will need to return numerator divided by denominator, and this will be the uh, likelihood is equal to this, which will be a vector of size and features, wherein for a particular class, you have a likelihood of each of the features in that example, and we return likelihood. Once we have done this, so this will return likelihood here, and each likelihood, it will take log of element wise logarithm and sum all of these elements, and then that will get summed with the prior probability. Once we have all the posterior probabilities for all classes, for a given example x, we'll do the argmax out of those list of posteriors and take the class of it to return it. So that's how, for particular example, we'll return a class here. So this will become an array of size of length of this capital X. Yeah, so this is all in the code of base NaiveBayes. What I'll do is I'll in the next video, while starting the next video, I'll show you the results after running this algorithm on this particular data. Thank you.